Hi everybody. Today we're going to look at graphing exponential functions. And I'm not in today, so I think this is a good skill that you will be able to, you're going to need in this learning target for exponentials. And we're also going to talk about the key features which we've mentioned. And the skill that we're going to show you today is pretty much the exact same skill that we had in the last unit when we were graphing radicals, where we looked at what's called a parent function, and then we plotted some points for the parent function, and then we manipulated them based on what was happening to the input values and the output values. So I'm going to go through the first question, and I made it as complex as I could so that you can see all the manipulations that could exist within this function. So the first thing we have to do is we have to identify what our parent function is. Our parent function in general looks like f of x equals b to the x. Now notice I don't have an a value. Well, I do. It's technically 1. Right? My a value will be 1. And then I don't have a plus c on the end. There's nothing here either. So I didn't move it left or up or down yet. So in general, in this case, my b value is 4. So my parent function would be f of x equals 4 to the power of x. Now I'm going to plot some points. Just like in the last unit when we were graphing either cube roots or square roots, there are some typical points that you can plot that are very easy for the parent function, and they come out to be 0, 1, and 2 for my input values. Now when I input 0, 1, and 2, you'll see I did in the calculator right here. 4 to the power of 0 is always 1. 4 to the power of 1 is 4. And 4 to the power of 2 is 16. Now what we're going to do is we're going to figure out what actually happens to my output values and my input values. Well, the input value, I'm only adding 1 to it. It's any value or operation attached to the x value, which is my input. So for the input values, like we've always done in the past, we're always going to be doing the opposite. So instead of adding 1, I'm going to be subtracting 1. So I'm at minus 1. Instead of being at 1, I'm going to be subtracting 1 from that. I'll be at 0. And then that'll put me at 1 for 2, except 2 subtract 1 gives me 1. For my output values, I'm doing two things. I'm multiplying by 2, and I'm subtracting 3. Now we have to follow the order of operations here, so what I'm going to do is I'm looking at my output values, and I'm going to multiply by 2, and then I'm going to subtract 3. So 2 times 1 is 2, take away 3, I have negative 1. 4 times 2 is 8, take away 3, I have 5. 16 times 2 is 32, take away 3, I have 29. So plotting these points, I'll be at negative 1, negative 1, 0, comma 5, so 1, 2, 3, 4, 5. That'll be my initial value. And then 1 comma 29. So 29 will most likely not fit on my graph. So what I'm going to do is I'm just going to go really as far up as I can and then put 29. There's my graph. Alright, so now there are a few things that we do have to be able to identify in our function to make an accurate sketch. We have to know where the asymptote will be. The asymptote, as we have previously discussed, is always going to be my c value. That shifts my asymptote up or down. For the parent function, my asymptote is at y equals 0, because it's plus 0. So what happens now if I have a negative 3? That shifts my asymptote down 3 units. So 1, 2, 3. and I make it a dotted line. It's not actually part of the graph, it's just more of a guide for me so that I can make my sketch become close to it in one direction. So as good as I can do right there. And there's my exponential growth function. So just to review, we plotted 3 points using 0, 1, 2, and that can work for all exponential functions. And we found out what happened to the input. We also found out what happened to the output. And we found our new points that it's going to be on our transformed graph. We located our horizontal asymptotes, so we had a point of reference, and we plotted our exponential growth model. It's a growth because my b value is greater than 1. If it's decay, it's between 0 and 1. Just keep that in mind. Now as we look at the next aspect, our y-intercept, our initial value, in this case we have our initial value, it will be at 0, 5. So 0, 5. Horizontal asymptote, that will be at -3. We should say y equals -3. Growth or decay rate, well, we don't have decay, we have growth, and it'll be 4. That's the number that you're multiplying by. Horizontal translation, did we go left or right? That means how is my input affected? Well, for my input, I was subtracting 1 from all my points, so that means I was going left 1. Vertical translation, did I go up or down? Yep, I subtracted 3, so that would mean I went down 3. For my domain, it would be all my x values. So I'm going to say from -infinity to +infinity. No matter what x value I pick, and as far left or as far right as I go, I will have an output. For the range, now I see that no output values can go below my asymptote. In fact, they can never reach your asymptote either. So your asymptote is always a boundary line for your range. So it's all values greater than my asymptote in this case, because the graph is above my asymptote. So it's all values greater than 3. So we say our least value that we'll have, not including it, would be -3. I said 3 just a second ago for the asymptote, I meant -3. And the greatest value will be +infinity. Now, one thing we did not mention here is the vertical stretch. When you multiply by 2, you should also make a note here that there is a vertical stretch by what we call a scale factor. So scale factor of 2. Alright, and that is graphing or exponential functions. That should give you every piece of information and tool in order to graph the next series of functions. I'm going to be posting an answer key later today. No, take that back. I'm going to be bringing an answer key to class tomorrow, so as you walk in, we're going to have an answer key out, and you can check these and see how your graphing went. Have a great day.